Okay, so I don't know if you saw this. This is the falling ladder problem video. It's really interesting. So this ladder on this side hits a table. This ladder does not. They're falling with strings in between them, and this one ends up going faster. And so I'm going to build a Python model, as I already explained. I think the issue is the tension when these strings, when these rungs hit, they pull down the part above them based on change in angular momentum. So together, we're going to build a model. So let's start with some ideas here. I want to model just one stick hitting the ground. Let me say how I would model a single ball hitting the ground. So suppose I have a ball like this, and it's falling. How would I model the interaction between the ground and the floor to make it bounce back up? Well, one idea is I'm going to over-exaggerate this, but suppose that I have this at y equals 0. Once the bottom of the ball, I'm going to over-exaggerate it, gets down here. Let's say, because Python doesn't know there's a floor there. It may see an object there, but it doesn't know to do anything. But once it gets below this level, then I'm going to say there's a spring force pushing up. F spring, or floor, F floor, is equal to negative K times, this will just be, actually it'll be the vector 0, y, 0. So y will have a negative value. So this is going to be a spring force pushing in the positive y direction, and K is the spring constant. So I will need to do a check. Is the ball below the floor? If so, then I have this force pushing up. And every time in my loop that I'm going to calculate, I'll set the force equal to 0, and then if it's not 0, I'll put it to this value. And then so the further it goes down, the greater that force is going to have to bounce back up. Now, a greater spring constant is going to work better. What about for a stick? For a stick, I'm going to do the same idea, except I'm going to look at two contact forces, one on each end. So let me draw my stick, because this is kind of important. There are 3 important points in my stick. It's a tilted stick. I have the center, and this could be any, the origin could be anywhere, okay? But I'm going to call this, I'll put it right here. There's my origin. This is R. I'm just going to call it R, the position of the center of the stick. And then I have the position of the end. I'm going to call that RL. So that's going to be, the R right. Cut through that vector right there. R right. That's the right side of the stick. And then I need to find the left side of the stick. R left. And if this has a length of capital R, why is it capital R? Well, because I'm going to use L for angular momentum, and I don't want to use the L twice. That's just me. So this would just be, if I have this tilted at some angle, this is really complicated, but this is angle theta, then if I know the location of the center, this vector right here, I can actually say R, the right-hand side is going to be the vector R plus R over 2, right, because that's this size, and then I have to multiply this by cosine theta, sine theta, 0. So I can find the location of that side. The other side is going to be the same thing, except it's going to be minus. So RL is going to be R plus, I did it this way, minus cosine theta, because it's on the negative side, and minus sine theta. Okay, so that's how I can do that. And then I can test if each of these will have an impact with the ground. And then I'll have a spring force. So really, there's going to be 3 forces on the stick. Let me draw another picture, because that picture's getting a little messy. 3 forces. So here's my stick. I have 3 points. And then I'm going to have 3 forces. In the middle, I'm going to have the gravitational force. I'll call it Fg, where Fg is equal to mg, and g is the vector 0, negative 9.8, 0 newtons per kilogram. Okay, normal weight stuff. And then I'll have the force on the left side, FL, and it could be 0. And then I'll have the force on the right side, F right, and it could be 0. Okay, so these two are conditional forces that depend on whether this is below the ground or not. So I'll have to check those. Okay, so now that I have the forces on the object, what can I do? The first thing is the momentum principle. So this says F net, which is going to be Fg plus Fr plus Fl, is the change in momentum. Now, if I take a small time step, then I can assume that during that time step, this force is constant. And if the force is constant, then I can say, I use my momentum update formula, solving this this is going to be P2, the final momentum, minus P1, the initial momentum, over delta T. And I'll say P2 is equal to P1 plus F, that's a vector, F net delta T. And that could just be the gravitational force. It could be some of these. I don't know. These could be 0. It depends on the situation. And then if I have the momentum, I can use that to find the change in position. So the center of mass of the object will be R2 is R1 plus P2 over M delta T. So this is my calculate my total force, update my momentum, update my position. I've done this a bunch of times, and I feel like I get bored saying it all the time. So it's my fault. I should just go into all the details, but sometimes I just get excited to do the fun stuff that I haven't done. But this is for the motion of the center of mass. Center of mass, just that point right there. Now what about the rotation? So this is the angle theta. Well, to find out the change in angle, I need to find the torque on the system. So we can use the angular momentum principle. Net torque is I alpha, where alpha is the angular acceleration, technically a vector. Now, the torque is only going to be in the positive or negative z direction. If this is in the xy plane, then the torque is either going to be out of the paper, which is the positive z direction, or into the paper. But I can calculate the torque due to these two forces. This force will not exert a torque about the center mass because it pushes through the center. So if I have this vector, I just realized I made a mistake. That's fine, I'll fix it. Okay, if I have that vector, then I can say, and this vector, I can say torque net is, I'll call this R, I need another name for it, R, and this will be, that's a vector, RLR. Then this is going to be equal to the cross product RRR cross FR plus RLL LL cross FL. That's the net torque. And that's going to be equal to I times the angular acceleration. The moment of inertia is for a stick about the center is 1/12 mr squared, the length of the stick. And then alpha, once I find the z component of alpha, I can say alpha, I'm going to do a similar process over here. Alpha is the change in angular velocity with respect to time. Once I calculate that, I can calculate the alpha, right, by dividing this torque in the z direction. This is a z component. So this is going to be equal to, I would say, torque net z over I. And then I can set that equal to omega 2 minus omega 1 over delta t. I can solve for omega 2. Omega 2 equals omega 1 plus alpha delta t. So in that short time interval after I calculate the angular acceleration, I can find the new velocity, angular velocity. And then I can do the same thing for the angle. Theta 2 equals theta 1 plus omega 2 delta t. So this is for the rotation of the center of mass, this 2. So that's what I need to do. Okay, so we got some coding to do. Let's get to it. Okay, jumping back over to Python, I'm going to give you the code as I always do. Notice right here, I just noticed this, and I had to do a little test run. In Trinket, it no longer says glow script, it says web vpython. So I kind of like that. I was surprised. I woke up this morning to a surprise. Okay, so let's start with some constants here. I need my G vector, 0, negative 9.8, 0. I need the length of the stick. It's a ½ meter. I'm just picking stuff here. The mass of the stick is 100 grams. And I need K. K is 500 newtons per meter. You want it kind of high, right? Because if the spring constant's too low, it's really going to sink down into that that surface, and I don't want to do that. I need I. I is 1/12 times m times, yep, that's m, times r squared. What else do I need? I need the ground. Okay, so I'm going to put this LG equals 0.02. That's the length of the ground, right? Because I want the top of the ground to be at 0. So I'm going to say the ground is a box. Its position is the vector 0 in the x direction, negative LG over 2 in the y direction, 0. So that means since it's the center of the box is going to be half the distance below, so the top of the box will be at y equals 0. And that's just going to make my calculations easier. And then the size is going to be, let's make this 1 by LG by 0.04, and I think that's it. Let's just run this, because whenever I make a new object, I like to run it. So there's my floor. Okay, nice. Okay, now I'm going to make my stick. So I need my initial position of the stick. Let's set that equal to the vector 0.40. I just picked something. And the initial angle of 25 degrees. 25 times pi divided by 180. Now let's make... I want to make the stick as a cylinder. And in Python, in web vpython, we're now going to call it web vpython. It says right here. In web vpython, I need the end of the stick and then a vector to the other end of the stick. So I need those two. I need that RL and RR, right? I need those two. So let's calculate RL. Let's do RR first. RR is going to be equal to R, the vector, plus R over... I already wrote this, right? I'm just typing what I wrote. Vector cosine theta, sine theta, 0. And it's not an object. It's just a vector. And then RL is R. Oh, that should be plus. Plus R over 2 times vector negative cosine theta, not theta, negative sine theta, 0. So now I have my two ends. I can make my stick. So I'm going to say the stick is a cylinder. Its position, I'm going to put it at the left side. So POS equals RL. And then the axis is the vector from that side to the other side. So this is going to be equal to RR minus RL. That's that. Now I do need the radius. Let's put the radius at R over 20. You can change that. It doesn't really matter. And then I'm going to make it yellow. Color equals color dot yellow. Let's see what that looks like. Okay. We're making some progress here. Okay. There's my stick. Okay. Now I do need the momentum of the stick. Stick dot P is, let's just say it starts from rest. Vector 0, 0, 0. I need the initial angular velocity. So let's say omega equals 0. It's not rotating at all. I do need those two. And then I need time. Yeah. Time. Is this big enough? Time is 0. dt is 0.001. So that's 1/1000th of a second, which is smaller than I normally do. But I need a short time interval for that collision, because the collision can be very short. So, okay, let's just make the stick fall. That's all I'm going to do. So while t is less than, let's say 0.5 seconds, rate 500. So I'm going to put the rate at 500. That's going to make it fall in half speed, since if the rate of 1,000 would be full time speed, but it's only half a second. So I'm going to make it run in slow motion. So the first thing I'm going to do is to calculate all these forces. So Fg equals m times g. Fl equals, that should be capital L, equals vector 0, 0, 0. I may change that, but for right now I'm going to put it at 0. Fr equals vector 0, 0, 0. And then I'm going to say Fnet is Fg plus Fl plus Fr. And so I like doing it this way. Oh, you can't see all that. I like doing it this way. Break it into pieces. You don't need one long equation. I mean, that's what Python's there for, so you don't have to do that. Okay, but now that I have the net force, I have the initial momentum, I can, I actually also want to calculate the net torque. Okay, so let's do that next. And even though it's going to be 0 because those forces are 0, I'm still going to do it. So I need that vector, let's call it RRR. It's going to be the vector from the center to the end, to the right end. So that's going to be RR minus R. And then RLL is RL minus R. Right? So now I have those vectors from the center, and those are what I need to calculate the torque. So I'm going to say torque net. I'm going to do this actually in one step. It's going to be the cross product, which is built into Python, and you can't see that. I just realized you can't see that. Let's do this. There, is that better? Cross, so the left one is going to be RLL cross FL. See how easy that is? Plus, now torque net is a vector. Okay, so I need to fix that. Cross RRR FR, RRRR. Okay. Next, I want to now I'm going to update the momentum. So stick.p equals stick.p plus fnet, which is, I'm just calling it fn, times dt. So this is the momentum. This is the final momentum. This is initial momentum. This is a make equal to sign, not an algebraic equal sign, so just be careful about that. Now I want to update the angular velocity. So let's calculate alpha. Alpha is equal to, and I'm going to use a scalar value of this. So I'm going to say torque net dot z divided by I. And now I can use that alpha to update the angular velocity. Omega is omega plus alpha times dt. That's exactly what I said on the paper. I'm just doing what I said on the paper. Okay, now I can update the position. So let's update R. R equals R plus stick.p times dt divided by m. So you'll notice that the center, I'm updating the center of the stick. But when I want to actually move the graphical stick, I have to move the ends. So I need to recalculate RL and RR and then draw the stick. So let's just copy this. I'm going to redo this, right? I know theta. Actually, I should calculate theta first, but it doesn't really matter. Okay, so I'm going to redo that. Now I know the position of the two ends of the stick. I need to update theta. Theta is theta. See, I should have done that before. Should I? I don't know. Let's do it before. I don't think it really matters. So let's say theta equals theta plus omega times dt. That's right. Now I'm going to update the positions. Now I'm going to move the stick. So stick.pos equals RL, right? That's the left side of the stick. And then stick.axis is going to be equal to RR minus RL, just like before. So, but those two values change, so that will change the stick. And in this case, there's no torque to begin with, so it shouldn't be a big deal. And then I need to update time. T equals T plus dt. So, you know, I like building a program like this where it doesn't do everything, but it should do something. And then I can kind of test if things are whack. So I'm calculating these forces, I'm calculating the torques, I'm updating the angular position, but it shouldn't change. So that's what I expect. I should probably save this, right? Bouncing stick Veritasium. Because how are you going to get the code if I don't give you the code? Unless you write it. Okay, running the program. Nice. Okay, so I didn't tell it to collide with the thing. I just didn't do anything. It didn't rotate, which is good because the torque was 0. So I think we're okay. Let's go, and now I have this stuff, right? I have these vectors, but I want to actually see if I need to change them. So I'm going to say this. If the position, the right-hand position, if r dot y is less than 0, then fr is negative k times r dot y. No, let's say this times the vector 0 r dot y 0. I can't do just r. I can't do that because then it'll give me an x component to my position, and so there'll be a force pushing it back the other way, and I don't want that. So that's my torque, my force in the right direction. And then so every time I get back to this loop, I'm going to set r to 0, and then I'm going to check if it's 0, right? If the position's below the thing, and I'm going to set it to this. Okay, next I'm going to need to do the same thing for the left side. If r L dot y is less than 0, f L equals negative k times vector r 0 r L dot y 0. So those should change if the stick's below it. So I think this should just work like that. Just putting that in there. I think it should work. Let's see. Okay. That's kind of awesome. Let's run it for a little bit longer because it's just like that. Say 0.9 seconds. Excellent. Very happy. Very happy with that. Very happy. I'm going to run it one more time and rotate it. Look at that. Okay, now I do need to check. Let's go ahead and check energy. Let's see if energy is conserved. So let's make a graph. So I'm going to put my graph up here. G1 equals graph. Title equals bouncing stick. I don't care if it's not capitalized. X title equals time. I'm going to plot energy versus time. And then the Y title is going to be equal to energy in joules, which I need to calculate. And then let's put the width at 400, the height at 200, since I have a small screen. Now I want to plot the kinetic energy, the rotational kinetic energy, the gravitational potential energy, and the total energy. I'm not gonna calculate the spring potential energy in the floor because that'll be a very short amount of time that goes in there, and it'll be fun to see. So let's say Fk is G curve, color equals color dot blue. I guess I could give it a label. Label equals, let's call it K. FKR is G curve, color equals color dot purple. Label equals K rot for rotational kinetic energy. FU is G curve, color equals color dot red. Label equals U, not UY. And then FE is G curve, color equals color. No, it's just black. But let's give a label. Label equals, let's just say E total. Okay, so I have those. If you want tips on graphing, I have a whole video on that. I'm not going to do that right now. So before I plot this stuff, I'm going to do it before the time. I need to calculate it. So K is the kinetic energy of the stick. I know the momentum of the stick, so I can calculate this as mag stick dot p squared divided by 2 times m, right? Momentum squared divided by 2m is the kinetic energy. But I can't square the momentum because it's a vector, so I have to take the magnitude of it and then square it. The rotational kinetic energy is going to be equal to 1/2 times I times omega squared. And omega is a scalar in this case. Remember, I already scalarized the whole thing. That's the rotational kinetic energy. U is going to be mgy, so that's going to be m times g, which g is a vector, so I need the scalar version of that, so I can say mag g. And then I'm going to multiply by the y component of the center of mass of the stick, so that's going to be r dot y. And then E is k plus k rot plus u. And let's plot everything. So fk dot plot tk, and again, making this so you can't see, f k, is that capital? Did I use capital? Yeah. This should be k. fkr dot plot tk rot fu dot plot tu fe dot plot te. Okay, it's bouncing. Okay, so this is pretty good. Let's run this for a little bit longer time, just so we can look at some stuff. Let's run it for 2 seconds. It's still in slow motion. Oops, I zoomed out. Okay, so this is the potential energy. Notice right here, energy is not conserved because of the collisions. And these are all the collisions. But in between those times and before and after, the total energy, the black, is constant. So that's a good sign. Notice here that the red curve shows the potential energies, which is a measure of the height. And this first bounce, it bounces back up to about the same height, but then it bounces lower, then it bounces higher. And so that's fine, because when it bounces, if it increases the rotational kinetic energy, it has less potential energy. So it doesn't go as high because it's rotating too. So that's kind of cool. Okay. Now, I want to fix something, because I don't want a perfectly bouncing stick. Right? This will just keep bouncing forever. Oh, and it flipped over. Look at that. Get pretty excited. I want it to lose some energy during the collision. So what I'm going to do is make a second spring constant, K. And imagine that when the spring is compressed, it stores energy in the spring of 1/2 kx squared. But then once it starts uncompressing, pushing back up, then it's only 1/2 k 2x distance squared. So it doesn't give back as much energy. So I'm going to use a weaker spring constant for when it gets repelled. Does that make sense? Okay. So that means I need to decide which spring constant to use here. So if I have this stick rotating, the rotation tells me whether it's pushing away or towards the floor, right? It should. So for this right side, I'm going to say if this is less than 0, then that's my spring force, right? But if omega is less than 0, then it's rotating away. And so it should be going away from the floor. And I'm going to say if omega is greater than 0, if omega is greater than 0, right? So omega is this way. You got it backwards. So that would be moving away. Then I'm going to say FR is negative K2 times vector 0 R dot Y 0. Right? Because that will use the weaker spring, it's moving away. Now over here, I'm going to say if omega less than 0, then FL is negative K2 times vector. And this isn't the best way to do it, but you know, I like to do things in a bad way, just to show you that bad ways do indeed work. Okay, so now I have 2 spring constants. Let's see what happens. I should save it. I haven't saved it in a while. Save. Very careless of me. Okay, run it. I like it. Okay, and let's look at the energy. So the energy, the first bounce, second bounce, third bounce. And you can change the each time it bounces, it loses energy until it stops. This is pretty awesome. You could make it less or more bouncy by changing the value of that second spring constant. There's a whole bunch of stuff you could play around with. But now that I have that first stick colliding with the ground, I can add another stick above it that's connected by strings, and then maybe 2 sticks above it, and see if we can reproduce the Veritasium falling ladder. But I just wanted to stop here with this and let you play with it. Code down below. Hope you like that. I had fun, and I'm looking forward to building the next part. The end.